All right, this week we're going to review average rate of change. Now, the average rate of change of a function over a defined interval can be determined by calculating the slope of the line that passes through the starting and ending points of that interval. So, as a quick review, average rate of change is a way of describing the change of a function over a specified interval, and it really doesn't care about what's happening in between the values of that interval. So, for example, let's take a look at this graph. So it's clearly not linear, it's kind of curvy. All right, so how is this graph changing? Well, if it's not linear, then the rate of change is changing. It's not constant. And in the case of curved functions, the rate of change is almost always changing. So how can we describe the general trend that happens in this function? So let's see. Let's find the average rate of change of g of t over the interval 0, 8. And if you recall interval notation, this just means starting at x equals 0 and ending at x equals 8, or the input. In this case, the input is t, so it's not x. So our input variable, or independent variable. All right, so let's see. What is the output when the input is 0? At 0, we have an output of 22. All right, and at 8, we have an output of 28. So how does this function go from 22 to 28 over the course of 8 seconds? Or I should say 22 degrees Celsius to 28 degrees Celsius over the course of 8 seconds. All right, so our starting point is 0.22, our ending point is 8.28, and all we have to do is calculate the slope or the rate of change of the line that passes through this starting point and this ending point. And so what we get is 3/4, which in the context of this problem means between minute 0 and minute 8, the temperature increased an average of 0.75 degrees Celsius per minute. Now, at no point, well, I don't want to say at no point, but it's not clear that at any point it was increasing at 3/4 of a degree per minute. That's not clear from this graph. But if you wanted to look at the general trend, over the course of 8 minutes, we went from 22 degrees Celsius to 28 degrees Celsius. So we could think of it in a simpler, more linear way as an average of 0.75 degrees Celsius per minute. Let's try another one. Find the average rate of change of g of t over the interval 3, 6. Now, why don't you pause the video and try to calculate this yourself. Pause the video now. All right, let's see how you did. So, starting here at t equals 3, the output is going to be 23 degrees Celsius. At t equals 6, the output is 27 degrees Celsius. All right, and if we can just kind of ballpark it, let's see, to go from this point to this point, that looks a little steeper, all right, than going from this point to that point. All right, so I'm expecting a rate of change that is greater than 3/4 of a degree, or 0.75 degrees Celsius per minute. So let's see what we got. So we take our 2 points, there's our starting point, there's our ending point. We want to find the rate of change between them. So we do our y2 minus y1 over x2 minus x1, and we get 4/3. Now in this context, 4/3 isn't very useful, so I'm going to use a mixed number because I want to describe a change in temperature. So between minute 3 and minute 6, the temperature increased an average of 1 1/3 degrees Celsius per minute, which is indeed greater than this 3/4 of a degree Celsius per minute. So that's rate of change in a nutshell. The two main ideas that you should take away from this lesson is that rate of change is just calculating slope. All you've got to do is pretend there's a line going from one point to another, calculate the slope, and that tells you, or that describes, the average rate of change over that interval. And the second thing you need to know or keep in mind is that this rate of change tells you nothing about what happens along that interval. It doesn't tell you the shape of the function, whether it's increasing or decreasing. It could do both over the course of that time. but you know nothing about anything that happened between the starting and ending points. You just know how to describe how you got from one place to another. So let's see this in action. All right, here are the prices of unleaded gasoline, the average prices from 1976 to 2008. Isn't this exciting? Unleaded gasoline prices. I'm excited. All right, let's see. There are 3 questions here. What I'd like you to do is read each question and try to answer it using average rate of change and see how you do. Let's pause the video and we'll be back in when you're done. All right, pause the video now. All right, let's tackle number 1. What was the average yearly increase in unleaded gasoline prices between 1976 and 2008? Pretend there's a question mark there. Okay, so where's our starting point? Well, our starting point would be right here, 1976, and it looks like the price is. Oh, I'm sorry. Let me start. So the question we're trying to answer is how do we get from this point to this point right over here? So you can imagine a straight line passing through these 2 points or going from these 2 points, and we want to find that slope. So we start with the first point in 1976. The price was 60 cents. In 2008, the price was $3.20. So if we wanted to describe this in the simplest way possible, we'd find the average rate of change. All right, using our formula for slope, we get the following. Simplifying this, we get 0.08125 over 1. So rounding to the nearest cent, unleaded gasoline prices increased an average of approximately 8 cents per year between 1976 and 2008. Now notice, during this time, the price increased, stayed the same, decreased, increased a little more, and then a lot. All right? This calculation tells us nothing about what happened between 1976 and 2008. It just describes in a very simple linear fashion how we got from one place to another. Number 2. During which 4-year period was the average increase in the price of unleaded gasoline the greatest? And what was the average increase during this period? So what you could do is analyze every 4-year period by calculating the slope, but in this case, you can just kind of ballpark it. It's pretty clear that the greatest increase, or the slope with the steepest line, is right over here. So analyzing this rate of change, the change in y is $1.40, and the change in x is 4. So $1.40 in 4 years. All right, so that simplifies to 35 cents per year, and that was the average rate of change. Notice, that's very, very different than when we analyzed 1976 to 2008. In fact, that's several times different. So analyzing different parts of a function can yield vastly different results. Now, let's think about this for a second. What was happening between 2004 and 2008 that might have affected unleaded gasoline prices? Well, I'm thinking, if you know recent history, the United States was involved in a military conflict in the Middle East. The Middle East is where much of the oil came from at that time. So this could have affected the prices. Now, does this describe a usual situation, a normal situation? We could argue this is kind of what's called in statistics an outlier. All right, this doesn't describe gasoline prices normally. Now, I'm not an expert in this area. I could be totally wrong, but let's pretend I know what I'm talking about. So let's consider this an outlier, and let's see what would happen if we just kind of ignored this one little data point, all right, this rate of change from 2004 to 2008, all right? So maybe we can get a general sense of how gasoline prices increase, quote unquote, normally without these extraordinary events. So, number 3, what would the average increase in price be if we disregard these 4 years? All right, so what would happen if we just calculated the average rate of change from 1976 to 2004? So now we're trying to find the slope of this line. Now this line looks a lot shallower, it's not as steep as the line that goes from 1976 to 2008. All right, because of these extraordinary values, that's going to change the average rate of change. This one I expect to be lower. And by how much? So when we calculate this, all right, what we get is approximately 4 cents per year. All right, and this example is just to kind of give you some practice using and calculating average rate of change, seeing it in a context, but it's also a secret lesson on outliers. All right, this 4-year period, all right, what it did to the average rate of change is it almost doubled it. All right, so if you wanted to know how do gas prices normally increase, you could make the argument, all right, that this analysis would give you a better idea. So if you wanted to predict something in the future, you might say, probably more like 4 cents per year rather than 8 cents per year, because hopefully we're not usually involved in a large military conflict that would affect gas prices. But again, I'm not even sure this data is valid. I got it from probably an unreliable source. So this is just for the purpose of this lesson. Don't take it too seriously. Okay, now why do we need average rate of change? So this is all building to a very important idea that you're going to study later on in your mathematical education, and that is how do we describe the rate of change of curvy functions? All right, so how do we do that? Well, we do it the same way we did for these other graphs and these other functions. All right, all we do is pick a starting and an ending point, all right, and we try to describe part of this curve. So what is the average rate of change between f of 0 and f of 2? Well, let's see. This is f of x equals 2 to the x. So what would f of 0 be? When the input is 0, the output would be 1. And when the input is 2, the output is 4. So we're trying to find the slope of the line that goes from this point to this point. So we set up our ordered pairs, we calculate our slope, and we find that the rate of change is 1.5, or 3 over 2, an increase of 3 units y changes by 3 units as x changes by 2 units. So I did the first one for you. Why don't you try the second one on your own? Pause the video. We'll see how you do. Pause the video now. All right, so what is the average rate of change between f of 1 and f of 3? So f of 1, the value of the function when the input is 1, is 2, and the value of the function when the input is 3 is all the way here to 8. So we're trying to find, all right, the slope of this line right here from this starting point to this ending point. So we identify our ordered pairs, use our slope formula, all right, to find the slope, and we can see that the slope is 6 over 2, which simplifies to 3 over 1. All right, so y changes by 3 as x increases by 1. Notice the slope over this interval is double that of the previous interval. And here are 3 situations. What I'd like you to do is analyze each one, identify your ordered pairs, and find the average rate of change for each situation. Pause the video now. All right, let's take a look. At 7 p.m., the temperature is 72 degrees Fahrenheit, and at 10 p.m., it is 52 degrees Fahrenheit. Find the average rate of change in the temperature. Now, in order to do this, you need to identify your inputs and your outputs, or your independent and dependent variables. Now, as time moves from 7 p.m. to 10 p.m., the temperature fluctuates. All right, there's not a causal relationship here, but usually when time is just moving forward and stuff happens, time is considered your independent variable, and the stuff that happens is considered your dependent variable. So to set up your ordered pairs properly, all right, we're going to put time as our input and temperature as our output. And I'll show you why in just a second, why this is so important. All right, calculating this, we get negative 20 degrees every 3 hours, or negative 6 2/3 degrees per hour. Now, let's say, so why was it important to put time as our independent variable and temperature as our dependent variable? Well, because in this situation, we describe a rate of change as degrees per hour. because like I said, we just kind of have this sense that time moves forward and the stuff that happens is it's not caused by the time, but it's definitely not the other way around. It would be very, very counterintuitive to switch these and describe this as hours per degrees instead of degrees per hours. Or degrees per hour. We discussed this in class. I gave you the example of why is speed always described as, let's say miles per hour or meters per second, and not the other way around. Mathematically, there's nothing wrong with that. It just seems weird, so we don't do it. All right, so number 2. In 1990, the value of a prized collector's coin was $12,500. In 2009, the value of the coin is $20,050. What is the average annual rate of change? So again, this is another example of time just moves on, and the value of a coin or a collector's piece increases. Now, in this case, you could argue that there is a causal relationship, because the older a coin is and the rarer it is, probably increases its value. A rare baseball card from 2 years ago might be worth less than a rare baseball card from 150. I'm sorry, that's too long. Maybe 100 years ago. Okay, so we know our independent and our dependent variables, so we can set up our ordered pairs. All right, in 1990, the coin was $12,500, and in 2009, the coin was $20,050. Using our slope formula, we can calculate that we get $7,550 per 19 years, which simplifies to approximately $397.37 per year. And finally, the third situation, Kevin's savings account balance changed from $1,450 in January to $1,140 in April. Find the average rate of change per month. All right, explain what your answer means. All right, so January, the months are our independent variable, and the savings account is our dependent variable. Plugging it into our, excuse me, our slope formula gets us $310. I'm sorry, negative $310 per 3 months, or approximately $103.33 per month. Now, I said explain what your answer means, and in this case, what does negative $103.33 per month mean? It means the bank account is decreasing by that amount every month. All right. So at this point, we've done a quick review of average rate of change. It's not an in-depth concept. You've got 2 assignments, a skills assignment and a performance task. Let's get started, and I'll see you at 12 p.m. For our online help session if you need to ask me any questions. All right, let's get started. Good luck.